All right, this it's fine. It will happen. All right. So yesterday we started talking, or Monday we started talking a little bit about alpha radiation. Yesterday, and again, the idea here is that sometimes atoms are too big, or they're not at the right ratio to keep them stabilized. So remember, protons are positively charged, and they're going to repel each other, and they're going to push each other away, and so they don't want to be together in the nucleus. But in order to have a nucleus, in order to have an atom, we gotta keep those protons together, and so we use neutrons to hold them together. But eventually, especially when we get to like 92, 93 protons together, it's just too much repulsive forces, and the nucleus wants to break apart. Okay, and when it breaks apart, it can release particles that we call radiation. And one that we talked about Monday was alpha radiation. Alpha radiation is a loss of two protons and two neutrons. So it has an atomic number of two and a mass of four. Okay, you add the four particles together. And alpha radiation is going to reduce the number of protons that are repelling each other in the atom. It's also going to reduce the mass of the atom, making it smaller. And as the atom gets smaller and smaller and smaller, it's become more stable. Ultimately, the most stable atom in the universe is hydrogen. Well, that's actually not true, but only having one proton, there's really nothing unstable about that. Iron is one of the most stabilized elements that have more than one proton, having about 26 protons in it. Iron is incredibly stable. That's one reason why our core of the Earth is made of iron, because it's a really stable atom. Okay? It has the right number of protons and neutrons really holding it together. So today we're going to talk about another type of particle, and we're going to talk about beta particles. So we saw this slide on Monday, and talking about the particle being released from the atom and how it can move through particles. Alpha radiation is actually pretty big. It's a helium nuclide. It's going to get stopped by your skin, by your clothes, by everything else. Beta that we're going to talk about today is a lot smaller. It's a lot smaller, about 10,000 times smaller. And beta, being a smaller product, it can actually go through clothes, it can go through skin, and it can go through stuff, and it can damage you in the meantime. Today we're also going to talk about gamma. Gamma is just pure energy that goes right through you because you're not made of lead or metal or concrete. And then neutron is another type on there. Okay, so as humans, we want to be careful about what type of radiation we're dealing with. Alpha and beta, we can protect ourselves from. Gamma, you can't really protect yourself from gamma radiation unless you're going to wear a big lead vest or something, which you can do, but most normal people are not going to be. All right, so today we're going to talk about electron particle being released, also known as a beta particle. Okay, so again, the atom itself, it can also lose electron particles or beta particles. Now, when it loses a beta particle, it is going to change its electrical charge, and it is going to the electron and the proton are going to turn into a neutron to balance each other out. And what's going to happen here is you're actually going to increase your atomic number by one, or what we're going to do here is a negative one on the atomic charge, okay, because it has a one negative charge, okay. So a beta particle is an electron, so that's really, really small. Electron is about 10,000 times smaller than a proton and a neutron, so this is a much smaller particle that's being released. Remember, electrons really do not have mass. They do have mass, but the mass is so small, 10,000 times, that we just say it's zero mass. Okay? That would be like you weighing yourself, but then there would be a feather laying on your shoulder. The feather doesn't change your mass on you. So we got a quick question here. So, Corinne, you got a question?
You were talking about like people having to wear a lead vest to protect themselves from the radiation. Is that just going to be any like solid element? Like, could titanium protect you, or is it just lead?
Um, no, it could be any solid metal on there. On lead is going to be one that absorbs a lot of particles in the process. That's typically what we use for radiation protection is lead. Lead is a very stabilized metal as well, kind of like iron. But lead is also very dense. And so, again, the particle is going to be shot through anything, basically. So again, everything has holes in it. Even lead has holes in it. And so if you have a really small particle, it can find those holes and go through it. Well, you have lots of holes in your body. You're a pretty big organism. Lots of big molecules, lots of empty space. Stuff can fly through you really easy. And so, and lead is super dense. And so lead doesn't have a lot of holes, so to speak. And so when that particle goes into lead, it's going to get stopped somewhere within a block of lead. You have a lot of empty space. Those particles can go right through you, and they go through you quite easily because we're a pretty big molecule. Do you have another question? Or?
No, that was all. Thank you.
No problem. But yeah, lead's also really cheap, and so you can actually wear a big lead jacket. If you're into nursing or X-ray technicians or anything like that, you go to a dentist office. Oftentimes, when you get X-rays radiation, they'll put a lead vest on top of you just to make sure the X-rays don't go through your entire body. And that's essentially what's happening when you take an X-ray. They're shooting radiation energy, and the energy is going all the way through your body. But in X-rays, they're not super strong, so they can't go through your bone. And so they can actually take a picture of that energy going through your body and being stopped by the bone. And you can essentially see the bone. So the X-ray goes all the way through the soft tissue and organ, but doesn't go through your bone, and they take a picture. However, though, if you get a lot of X-rays, so if you are a nurse or a dental assistant or something like that, and you're in there in the X-ray machine all the time, that can cause a lot of damage going through your body all the time, especially damage to your reproductive system. Remember, your gametes are only half cells, and they have half your DNA in them. So that's half of your DNA. If your gametes and your sex cells, if they get damaged, and you go to try to have a baby later on in the future, the sex cells are going to be damaged, might not even be able to have children, or you might have children that have mutations or things wrong with them. So that's the reason why you really do want to protect yourself if you're around X-rays a lot. Getting 1 or 2 or 10 a year is not a big deal, but if you're doing, I don't know how many X-rays those nurses do a day, but if you're doing 20, 30, 50 a day, that's a lot of X-ray radiation you want to protect yourself from. But again, X-rays are not as bad as the gamma radiation we're going to talk about next. Gamma is even worse. But that's not normal. Gamma radiation is not something around you. But the first one we talk about, so this one is an electron radiation. Electrons are pretty small. They can go through your body tissue, that kind of stuff. And so when we get a sunburn, you're being burnt by ultraviolet beta radiation. So it's ultraviolet and it's beta. So it's a little ultraviolet electron that's going into your skin, and that's what's cooking your skin essentially. It's damaging your skin cells, and your skin cells are trying to repair themselves by creating heat, and it kills off the damaged cell. So your body is protecting you by burning the skin off that's damaged. So that's essentially what a sunburn is. Okay, that's why you get tan, and your body is trying to protect yourself from it. So if you want to protect yourself from beta radiation, the shielding there, we need some kind of like metal foil, or like a really dense jacket or something like that can protect you from beta radiation. This is a weird fact, but you can get sunburned through clothes. People don't realize that very often, but when you buy sun clothes or winter or summer clothes, a lot of your clothes will have a SPF number on them, and you have to be careful about what SPF number you buy. Because again, your clothes have holes in them. So that radiation can go right through those little holes and burn you even with clothes on. Okay, it takes a lot of sunlight to do that, and takes not very good clothes, but it can happen. All right, so note the mass number on top is 0 for a beta because electrons essentially don't have mass, and the atomic number at the bottom is a -1 because electrons have a negative charge. Okay, so it's not a proton, positive one. It's an electron at a -1. So beta is going to be a -1 in our balancing. So for example here, we end up with this radon, or this radium here, and we actually have a mass of 228, atomic number of 88, and then that can undergo a beta particle. Note that the mass stays the same on top, 228 to 228. But this time the atomic number went up, actually, okay? And what's happening there is that a proton is being created in this process of losing that electron. And so we have 180, or we have 88 atomic mass here, and now we have an atomic mass of 89. And we make a new element that's more stable. Okay, so this ratio of 88 to 28 is less stable than this ratio of 89 to 100 to 28. Okay, so again, it's all about this ratio of protons and neutrons. What's going to make us the most stable? And so this ratio of 89 to 228 is more stable. It's not going to break apart as much as this ratio over here. Okay, alpha particles are very fast moving, but they're much smaller than the alpha particles themselves. All right, so in an equation form, we will write it out like this. Again, the radiation particle is being lost or gone, so it'll be on the right side of the equation. So, for example, we have carbon 14 here. Mass of 14 stays the same because of 0 over here. We had 6. So what plus -1 will give me 6? Well, it's 7, so the atomic number is going to go up. So this ratio is more stable than that ratio there. Nucleus doesn't lose or gain electrons; it's just decaying to an electron. It's changing. Okay. So on let's see what that. Okay. Now gamma radiation is also emitted. I don't know if you saw that in here. So this is a gamma radiation or neutrino radiation on there. Is also typically emitted, but gamma radiation doesn't have any mass. We'll talk about that in a second. Okay. Carbon 14 dating. Carbon 14 dating is kind of what is happening here. Carbon 14 emits beta particles and it breaks down over time. Carbon 14 has a half-life, I think, of 10,000 years. So when you die, the carbon in your body is eventually going to change and you're going to lose your carbon, but it takes about 10,000 years to lose half the carbon in your body when you die. So if I dig up some bone and I see that, hey, half the carbon changed to nitrogen, then that bone is about 10,000 years old. If I dig up a bone and I see that there's almost no carbon left in it, it's almost all nitrogen, then I'll say that bone is really old, okay? Because it took a really long time to get to almost no carbon. If I dig up a bone and I say it's almost all carbon, well, that's a very young bone that we dig up. Carbon dating is great for living organisms because they're like animals and things like that, but it's not great for going way back in time. So if we want to go way back in time, we do what's called uranium dating. Uranium does the same thing. Uranium turns to lead. So if I look at a rock and it's got a lot of uranium in it, then it's a young rock. If I pick up a rock and it has a little bit of uranium, but mostly lead, it's a very old rock. And we can actually tell how old rocks are from uranium dating. So looking at elements that decay naturally over time, we can actually tell how old things are. We can calculate how old things are on with them. So, another type of radiation called gamma radiation. This is just straight up energy. Okay, gamma radiation is released during all parts of during radiation, but we don't want a lot of gamma radiation. It's just pure high energy electromagnetic radiation, kind of like an X-ray, but it's one step up. It's even stronger, more powerful than X-rays. Gamma is just energy. It's not a particle, so it has no mass. It has no charge. It has no atomic number, nothing. Okay. So on there, we say that gamma radiation is 0, 0, 0 on top, 0 on bottom. It's just energy being released. Some things do release energy naturally, and it can release a lot of gamma radiation. Gamma radiation is the one that's really bad because it's not a thing, so it's just going to go straight through you. And so it takes a really thick object to slow that energy down, okay, before it goes all the way through. You're not thick enough or dense enough to stop that energy. So the gamma radiation literally just goes straight through your body, and you don't feel it. You don't even notice it. And then it just basically puts a nanoscopic hole right through your body. It doesn't even, you won't feel it, you won't notice it, but that hole can damage your cell, it can damage your DNA, etc. And so again, if you're talking about getting gamma radiation or X-ray radiation through your cell that you're producing children with, it can damage that DNA and might not be able to have kids. If you get enough gamma radiation going through your body all at one time, it can kill off cells. Some cells that don't repair themselves are like eyes. your eye cells don't repair themselves. So one of the first things that will happen with gamma radiation is that people will start to go blind. Okay, the rods and the cones will start to go away because you're putting little itty bitty holes in the eye cells and they don't repair themselves. And of course, if you're exposed enough, you'll start having internal bleeding and everything else. And again, you're putting holes through your body essentially. Then you can die very short term from high gamma radiation. So that Bruce Banner movie where you got all that gamma radiation and turned into the Hulk, nope, that's not going to happen. That's not going to happen at all. So, Teenage Mutant Ninja Turtles, when they drink the gamma radiation stuff, they turn into karate fighting turtles. Nope. All right, so just to kind of wrap up the particles here. So alpha particle is a helium. It's got a mass of 4 and atomic number of 2. And we say helium or A for alpha. It does have a +2 charge, so you are losing 2 protons in that process. A beta particle, no mass, it's super small. And then it has an atomic number of -1 because it's a -1 charge for an electron. Gamma radiation, we say it's 0, 0. No mass, no charge. You just say gamma, and nothing changes. It's still the same element, same atom in that process. All right, so today we are going to work on part B of our, where'd it go? I had it. But today we're going to work on part B together as a group in our breakout groups. And again, we're going to kind of make sure that we are typing in correctly. Where is it? All right, let me pull up the worksheet real quick, just so that we kind of make sure we all understand how to type it in. Because again, we went over it yesterday, but a lot of kids were still turning in stuff that I couldn't see, I couldn't read, I couldn't grade. So I'm pulling it up here. Taking a minute. So again, when you do your boxes here and you're trying to do a beta radiation, which I think that's what this one is, yeah. So again, you have to click on the box and you have to type in these boxes what it is. So the top box is going to be 0. And again, you might want to make this a little bit smaller so that we can actually read it. Okay, so go in there and actually make it smaller. So the top has a mass of 0 and it has a charge of -1. Again, I'm going to make that a little bit smaller. Okay, and we call that a beta. Someone can put a B in there. You can also put an electron in there. So real quick, in the chat box, what plus 0 gives me 14? Yeah, 14. I messed that up. So 14, right? And so again, I'm going to make that kind of smaller just so I can read it in the box. All right, what plus -1 gives me 6? 7. Yep. 7. Again, I'm going to make that a little bit smaller. And what is element number 7? And that is going to be nitrogen there. So then we'll save and close that. But then now you can kind of see the numbers. And that's what I can grade when you actually fill in this worksheet. So again, some of you, when I go to grade it, I'm like, hey, you might want to fix that box. You might want to type it in better. You know, that's what I'm doing. Just fix it, turn it back in if I do that to you. All right, let's see what we got. Comments, yeah, say, yeah. But using both while at the same time, yep, it would. Yep. Yeah. That's essentially how a bomb shelter works when you think about nuclear bombs. A bomb shelter basically works by stacking lead and concrete together. And so you don't need a big chunk of lead. That'll be really expensive. That'll be really heavy. But they basically take a thin piece of lead, big concrete, thin piece of lead, big concrete, and they stack it all up so that they can absorb as much radiation as possible. Most radiation that you're exposed to, you're not going to get that. It's not going to be that much. So we're not really super worried about it, but you do just want to make sure you're not in it all the time on that. So I'm not trying to scare future nurses and things like that. Because it's okay. It's not, the walls are safe enough. They are protecting you. Now, if you go work at a nuclear power plant, or if you go work somewhere like that where you're dealing with nuclear radiation all the time, you'll be trained in how to do all that safe stuff and stay as safe as possible. So, all right, let's go into breakout rooms. Let's work for about the next 9 minutes. That's about all the time we have. And help each other out with this. And again, if you don't know how to do the boxes thing, talk to your friend, talk to me. Let's figure out how to do these boxes and help each other out. All right, when you're in the room, talk to each other, have fun, be friends. If you're done, help each other, help other kids. But then if everybody's done, talk to each other, be friends. Just like you are in school when you're sitting at a table. You don't talk about science all the time. You talk about other stuff too. All right, go have fun. Help each other out. Eventually. It's still closing. I think we've still got one room closing up still. All right, I think everybody's back. All right, so we have about 1 minute left here. Tomorrow we will spend the first 10-15 minutes working on this like we did on Tuesday. Again, make sure that we're not falling behind. We have, I want them to, I'm meaning for them to be small, but make sure we're not falling too far behind. I'm trying to give you guys time to make sure you get all your stuff done. If you do feel yourself falling behind, spend some time, doing it for homework or asking for help or whatever it is. Okay. All right. So tomorrow we will do a Thursday quick little professional habits assignment. We'll get time to work on this. And then you guys have a quiz on Friday. It's still locked. It'll be locked. It'll be unlocked Friday morning. You guys need to take it during class time on Friday. So it will be locked. Study. Okay. Study. Look at your resources. Have your notebook. Look at your activities that we're doing right now. You're going to have quiz questions over the notes, over the activities themselves. So please take a look at both of those. Okay? All right, I'll see you guys, and we'll talk more about it. I think both I'm gonna do Friday or Sunday. It should be on your Sydney. It should be on your. It should have a due date, but I'm not exactly sure off the top of my head.